Alright, hello everyone. So today we're going to be talking about carbon-to-carbon coupling reactions. Now these reactions are very important in organic chemistry because they allow for the formation of carbon bonds within molecules, which is very, very important for making larger structures, especially in pharmaceuticals. And there's a bunch of different kinds, and they're all named after the people who kind of pioneered and discovered them. So we're going to start out with Sonogashira, and Sonogashira took a compound like this one here, and what we can see, I've highlighted here the bonds that are going to be bonding to each other in the new compound. So the carbon that is bonded to this iodine right here, as well as the carbon that is bonded to the hydrogen in our reaction. And so what you see here is that this top molecule is what's actually reacting, and these other molecules are helping to assist the reaction and catalyze the reaction. And what's characteristic of the catalyst of Sonogashira is that we have copper right here. And so that if you see copper iodide or anything that has copper in it as a catalyst, you can immediately know that that's a Sonogashira reaction that's taking place. So then what we see in our products is we see that this carbon over here is still right here, and this carbon right here is now bonded right here, this one right here. So that we have made a carbon-to-carbon single bond through that process, and it has been catalyzed with copper. And this is a more generic form. What you can see, we have a general alkyl halide and a carbon chain right here with a triple bond. And what we do is we put it in the presence of copper again, and a base, which is our base up here, is this right here. And so then we form a carbon-carbon bond. Alright, so moving down to our next type of reaction, we have our Negishi reaction. So with our Negishi reaction, this is very important. We can see that there is the presence of zinc. And if you see that there's a presence of zinc, then you know immediately it's Negishi, just like we did with copper and Sonogashira. And so basically what this reaction does is similar to what the Sonogashira reaction does, except for we are going to substitute in a hydrogen right here, where before we had a halogen. And so the two carbons that are going to bond to each other are going to be this one that's bonded to our zinc bromide, and this one that's bonded to our chloride. And so over here you can see those are the two carbons that bonded. And so that's also very important because it's another way of creating a carbon-carbon bond with a different type of other reactant. This is a different type of compound. It is also an aromatic, as you can see by the ring structure. And this is also done in the presence of heat, so 65 degrees Celsius, whereas the Sonogashira was not in the presence of any specific heat. It can be done more broadly. Moving down, we have our steel reaction. So what is characteristic of steel is that we have the presence of tin right here. So anytime you see tin, we're going to know that it is a steel reaction, and that is where the carbon is going to bond in our product. So again, we're going to have this carbon right here is going to bond with this carbon right here, which is again attached to a halogen. That's another thing that you can look out for, is the carbons bonded to halogens are usually the ones that are going to bond to create the new carbon-carbon bond. And again, this is in the presence of palladium as a catalyst. Like many of these reactions, they all have palladium as some form of catalyst. And this one again is done in the presence of a certain heat, 80 degrees Celsius. And then what we can see from there is that these are going to be the two carbons that are going to bond to each other and create this new compound. And that's really important as well because it's connecting a ring structure to a line structure, and that's very strong in a lot of organic chemistry and a lot of pharmaceuticals especially. Moving down, we go on to our Suzuki reaction. All of these that we've looked at so far are relatively similar, and Suzuki's no different. What we can find in our Suzuki reaction, though, is the presence of a boron attached to two OH groups. So that is characteristic of our Suzuki type reactions. So if you see that group that I just highlighted right there, then you know it is a Suzuki reaction. And again, we have our halogen over here. So we know that the halogen carbon, this one right here, is going to bond to the carbon attached to that boron and two OH groups. So then what we get in the presence of palladium as a catalyst, and then some other reactants to help move the reaction along in our steps, we come to this molecule right here. So again, let me zoom out for you. As you can see, this carbon right here and this carbon right here bonded together right here and right here. And then we get that new molecule that's, lots of aromatic groups put together. You have multiple rings, and it's very important again in pharmaceuticals. Moving on, we have Heck, which is another type of reaction, but is a little different. So far, what you've probably seen from all of these reactions is that they have some form of metal or transmetallation step. And again, those are the things that are specific to each reaction that I talked about. So for Sonogashira, the transmetallation step is the step that involves the copper iodide in this case, so that copper. For Negishi, the step that is the transmetallation step in the reaction mechanism is involved with this zinc, in this case the zinc bromide. Steel reaction, same thing, the transmetallation step occurs where the tin is located. And then the Suzuki reaction, the transmetallation step occurs with that boron and two OH groups. Now for Heck, it is also a CC coupling. However, it does not have a transmetallation step like the others. So what we're going to do, basically, we're going to take our halide right there, and we have a carbon chain with a metal, and we put that in the presence of palladium as a catalyst again, and we're going to get that carbon that was bonded to the metal bonded in that position of the halogen. So here's a good example. We have this iodine right here bonded to this carbon chain. So then what we see is that in the presence of palladium, we get this bond right here, and then we've made this whole molecule right here. And so what we're going to go over here do is kind of just look more at the mechanism of the Heck reaction specifically. So where we start out with our reductive elimination step to start. So that is where we take our original compound and we put it through this process called reductive elimination, where we take out a hydrogen attached to a halogen, leaving us with just our RER and our halogen. And then what we're going to do is we're going to put that in the presence of palladium 0, and through oxidative addition, which is our next step, we insert the palladium in between those two molecules. The next step that we go through is we're going to take one of these, and it's going to go in and substitute and associate with that palladium that's in the middle, again right here. So these are going through electron transfer, and they associate, and then what happens is a syn 1, 2 insertion. Now what that means is that what we had here, this right here, has carbons 1 and carbon 2. So then we're going to go over and insert the syn 1, 2 insertion. What that means is that if you see right here, we have, I'm just going to highlight a little bit to see a little bit better. This is our molecule that we're inserting, and this is where it ends up. So then we've inserted it at the carbons 1 and 2 positions. Again, those are those right there. And that's why it's called a syn 1, 2 addition. and syn refers to the stereochemistry, where the stereochemistry is retained. So then what we have is that has been inserted, so then our palladium is off to one side, our palladium and our halogen is off to one side, and our AR is off to the other side with hydrogens attached as necessary. The next step in that process is called the beta elimination. Now, the beta elimination is a very important step for this process, and it can only happen if the syn 1,2 insertion happens, because the beta elimination needs to have syn conformation in order to occur. And it also needs to have what is difficult to see now that I've drawn all over it, but this right here, this arrow, and let me do that a little bit better, we'll do it in a different color. This arrow right here. What that's showing is that there is free rotation about that carbon-carbon bond in the middle of that atom. And that free rotation is what really allows the beta elimination to occur. So, beta elimination. The whole process is based on the positioning of the carbons. Actually, I'm going to go back to red here. So, from our previous molecule, we have our carbons here and here. This is an alpha carbon, this one right here. And then this other carbon over here is called a beta carbon. So, the beta elimination happens at the beta carbon position. Now, how it works is through electron transfer. So, the electrons come from this bond, go into that bond, and then it kicks out this hydrogen over to the palladium, which then separates the palladium. And as you can see also, before I continue, you can see that this rotation has occurred because our AR is now back into the page, and one of our hydrogen groups is out of the page, whereas down here our AR was out of the page and that hydrogen group was back. So with that rotation has occurred, and so that's what allows for the beta elimination to occur. And then from there, once that hydrogen gets kicked out, we come back full circle to our molecule that we had before with our AR and our CO2 ET, which is carbon dioxide and ethanol. And then we have our PD and our X and our H left over. So the H is come out and it goes through that process again. Productive elimination, oxidative addition, followed over to the syn 1,2 insertion, and then because of that free rotation around the carbon bond, we get that syn beta elimination step. And that only happens because of that rotation about the carbon bond. Now, HEC is a very, very useful reaction because it's so unique in the fact that it does not require any specific metal to occur. It just requires that beta elimination step and that carbon rotation. So it's utilized a lot in pharmaceuticals and in organic chemistry in general. Moving on, we have Buchwald-Hartwig. Now this reaction is a little bit more complicated. So we're going to take a similar compound we had before with a halogen, and we're going to put a carbon group in any position on the carbon chain. It can be ortho, para, or meta, and that's what this line means right here, is that it just means that we aren't specifying where that carbon group is attached. And then we are going to put it into a reaction with a nitrogen bonded to two different carbon groups and a hydrogen in the presence of palladium, as well as some other compounds, specifically dioxane, and it's going to be done at a specific heat of 65 to 100 degrees Celsius. And what that allows for is for the reaction to occur. So what we get is a product. Again, we have that R group in any position, ortho, para, or meta, in relation to that other group coming off. And what we've done is we've substituted this group right here into this position through this reaction. So then what we get, basically on that other product side, that H and that F comes off. So then we get that as a secondary product. But what we've gotten more importantly is a carbon to nitrogen bond. Now this is a little bit different than what we've looked at so far, but this carbon to nitrogen bond is very important. And it's the Buchwald-Hartwig is one of the ones that allows us to get a carbon to nitrogen bond in such a way. And so I'm going to show you guys another example down here of an actual compound that is used pharmaceutically with carbon-nitrogen bonding. So this molecule is pretty large, but the mechanism that we run this through also allows for carbon to nitrogen bonding. Specifically, you can see it right here and right here, as well as right here. So this only happens because of the Buchwald-Hartwig reaction mechanism and the way that they worked on making it so that carbon-nitrogen bonds were possible. And this is actually called sopranox, which is an antifungal compound that is, used in like foot creams or whatever you need to fight fungal infections. Finally, we're going to talk about NAS, or what NAS stands for is going to be, I'm going to write it over here, is NAS. We have nucleophilic aromatic substitution. Now, there are two types of nucleophilic aromatic substitution. The first type is relatively simple, where we take a compound like this one right here, and we put it in the presence of a nucleophile. That's what we have right here, nucleophile with lone pairs of electrons. And then those lone pairs will come in and attack this halogen group here, which then sends electrons through the ring and up to this nitro group right here. And then that nitro group gets more electrons when then it's the nucleophile, has now attacked right here. And we see that bond happening. And the double bonds have been rotated to accommodate for that additional electron density. And as a result, there's now a negative charge on this top nitro group up here. And so then those electrons will send back through and back onto this chlorine group, because the nucleophile just attached and is stronger than the chlorine group. So the chlorine group is what's going to be kicked off the ring first. And so then what happens is we end up with this right here. So we've got our nucleophile who has just attached in that position where the chlorine was, and through that electron motion back and forth through the ring, we now have a negative chlorine ion just separated from that original structure. Now, the second type of nucleophilic aromatic substitution is a little bit more complicated. So we're going to look at that now. So we're going to start off with this compound right here, which has a nitro group and a fluorine attached, and then we're going to run it through the presence of NaOCH3, which just gives us a nucleophile to then, push the reaction forward. So what we do is this nucleophile is going to attack that fluorine group, because fluorine is the more electronegative atom than the nitro group. And so in this case, it attacks that fluorine group, and I skipped a step from what I had before where that OCH3 and the fluorine are both there. But I think you guys get the concept. So the OCH3 then attaches in that position and kicks off that fluorine, which becomes an F- ion, which then hooks up with this Na+ ion to form sodium fluoride. And then what we get is that mechanism here, so I'll show it to you guys right down here. We get that OCH3- nucleophile coming in, which kicks into this position right here, which then kicks these electrons around and gives a lone pair of electrons right here with that negative charge, which then kicks the electrons around down to here. We have that right there with those double bonds. And what this actually is right down here is a very important part of this. Is called the Meisenheimer complex. And it's the way that the electrons can move around and kind of create different bonding. So once those electrons are down in that bottom position, they actually will kick out of the ring onto this bond between the carbon and the nitrogen and create a carbon-nitrogen double bond. and which will in turn kick off one of those double bonds from that oxygen here and create a O- charge. Create two O- O- charges instead of just one. That's an important little subsection of nucleophilic aromatic substitution, and Meisenheimer complexes are part of what make the reactions occur because of all that movement of electrons. So then from that step, we're going to move on in this direction, and we're going to get those electrons are going to keep bouncing around until they get over to here, and they're going to kick back into the ring again, and that's what we get, these nice full double bonds throughout the ring again. And once they've kicked back into here, they kick back on that fluorine, and that fluorine detaches from that group, and we get that NAF, as I showed it before. And so that is the elimination step for that fluorine. So what we do, the reason it's called nucleophilic aromatic substitution, is we take the nucleophile, nucleophilic, and we put it onto an aromatic ring, so aromatic, and it is substituting in from a group that we already have. So nucleophilic aromatic substitution. We have the nucleophilic, we have the aromatic, and the process of substitution. Oops, I totally just wrote that. Nucleophilic aromatic and the substitution. So then overall we have that and the A and S, nucleophilic aromatic substitution. Alright guys, thank you so much.